So now I'll talk about some examples of inner products, and this basically covers all the high spots. So the standard inner product on Fn is just, like I said, you take the kth coordinate of u and the kth coordinate of v, and you multiply them together and you sum them up. And if you're dealing with complex numbers, then you need a conjugate on the second one in order to make sure that things work out. So the next thing that you can do to make it slightly more spicy is you can add some weights. And when you do this, you need to make sure that the weights are positive, or it can break definiteness. So what you do is you just have now k equals 1 to n ck uk vk prime. And here, so the ck's need to be strictly positive. And notice in this assumption right here, it's implicit that I'm assuming that ck is in R as well. So they need to be positive real numbers. And so the reason why they need to be positive is that if some ck is 0 or negative, then it will not be positive definite. So what else do we have? Okay, now we can do sort of like the more general type construction. And so let's see, so for this one we need a bit of background. So suppose that I've got a transformation, an operator rather, which has strictly positive eigenvalues. And I guess I should say those are the eigenvalues of the complexification if required. And suppose that A is the matrix of T in some basis. Okay, so now the assumption here that the eigenvalues are positive, this is going to be to ensure that we have positive definiteness. And then I'm also going to require that A is Hermitian. And so Hermitian means that A transpose is equal to A conjugate. So again, if it's the case that F is the reals, then we're just looking at a symmetric matrix. So this is something that's not quite symmetric. It's equal to its own conjugate transpose. I could put the conjugate here. I could put the conjugate here. So it's equal to its own conjugate transpose. Okay, so with that, then I can define an inner product as being now the sum j equals 1 to n, k equals 1 to n, uj a v k conjugate. And it actually turns out that on Fn, any inner product is going to be of this form. So the way that you should think of this is you have u transpose a v conjugate. So there's going to be like a row vector, and then a square matrix, and then a column vector. By the way, this is the reason why a lot of people, especially if they're coming from a physics background, actually define the inner product differently. They define it so that the conjugate is over on the left argument, so that it's linear in the second slot and conjugate linear in the first slot. And the reason why is because that gives the interpretation that this is an element of the dual space, And this is an element of the original space, because we usually think of vectors as column vectors, and we usually multiply with the matrix on the left. Anyway, just throwing that out there. So you'll see other conventions, especially if you look in a physics textbook. So let's see, leaving that as it is, just because of this thing about Hermitian matrices here, just as a side note, a Hermitian matrix with positive eigenvalues is called a positive definite matrix. And so this corresponds to a physical process or transformation in which the output Tx is in the same general direction as x. So in other words, if you have say axes like this, and we have here's your input positively oriented like that, then that means that the output is gonna the output is gonna live somewhere in this positive half plane. That's a pretty crap picture of a plane. Maybe that's slightly better. Oh, sorry, not plane, half space. Yeah, okay, let me ditch the horrible. Okay, so if we take this plane right here, and then we take the collection of points that's in this plane, but also anywhere to the right, that's what we're saying. Okay. So let's see. So now these are all for Fn, but we can do other things. So we can also look at the standard inner product on the continuous functions on the set X. So this, for example, if we're looking at a vector space of polynomials, we could do this. But also for other functions, and in fact, they don't have to be continuous functions, they just have to be functions on which the integral is defined, because that's how we define the inner product. The inner product of u and v is, so we take the x coordinate of u, the x coordinate of u, and the x coordinate of v, and then we add them up. So now there's an infinite addition, it takes the form of an integral. But it's the same basic idea. And for the case when u and v are complex valued, we need to incorporate a conjugate. So we'll have a conjugate here on the second one. We also have the diagonal inner product on Cx. So this one comes up relatively often. You'll see it if you take differential equations, for example, especially if you take partial differential equations. And so in this situation, let's see, we're going to take, oh, and I forgot something right here. I forgot to write that this is the integral over x. And we need the same thing over here, so this is going to be the integral over x of ux vx conjugate, and then we can put in a weight function, sigma x, as long as sigma is everywhere strictly positive. Okay. So you should see the parallel, right, with the ones that we did above. Okay, now what are we going to do more generally? Okay, well, suppose that f is a positive definite function. Oh, I forgot my is a positive definite function. And being a positive definite function, this means that if we evaluate it at finitely many points, we get a positive definite matrix. So, more precisely, if we take any finite set x1 through xm in the domain, and we define a matrix to have jkth coordinate equal to f of xj minus xk, then we get a positive definite matrix. And you would think that sounds like a crazy condition. How on earth are you possibly able to check such a thing? But it turns out that there's deep theorems. So in fact, there's a famous theorem by Bachner that says that this is going to be true if and only if f looks like the Fourier transform of a positive measure. This isn't the case when f is continuous. So for continuous f, you get something which is positive definite if and only if it's the Fourier transform of a positive measure. And if that sounds like a foreign language, don't worry about it too much. What I mean is that f of x looks like the integral of e to the minus 2 pi I c x. Then we have some mu as our measure, and you can think of that as a positive function. That's a bit of a lie, but positive function. It's true if it is a positive function, so that's good enough for now. So suppose we've got a positive definite function. Then we can define the inner product to be the double integral over x cross x of u fx minus y vy conjugate dx dy. And so now most of the time we won't use these fully general ones where we have the matrix product or where we have this double integral. But the diagonal weighted cases will be useful from time to time for sure.